So I'm Paul, and I'm from Simply Rhino. We're the UK providers of Rhino software. We've, for the last over 22 years now, we've been focusing on Rhino and the key plugins for Rhino. We've worked with the AA school for many years, and Photius works here, that we've helped him with the supply of Rhino licenses for students over many different occasions. And we also offer classes in Rhino, Grasshopper, etc. And you will see those details on our website. Just here, if anyone wants to scan that code, that will then, it will take you to a page where you can register, and then you will hear news then of all the events, these sorts of Grasshopper meetings, Rhino user group meetings, and also the big event which is called Shape to Fabrication, which will be back next year. Okay, so other than that, I'm just going to hand you now over to Milad.
We are hosting this session with a great lineup of speakers. We have Miriam from MakerCO Collagen, digital lead in the office, going to talk about how they use these computational pipelines in their day-to-day jobs. We will then follow by two of our recent graduates, Pooja and Jonathan, that as a part of their master thesis, they have developed a very well-polished pedestrian simulation. Whoever is in need of pedestrian simulation, heads up. Then we go with Olga from Imperial College and Rion Labs, who will talk about how they use these pipelines for product design phase. And we will end with Elif and I presentation about our recent research in biomaterials and how we use these workflows in our processes. Just a few housekeeping notes. We're gonna run the presentation back to back, around 20 minutes each. And then we will have a panel discussion over here, and we'll open up the floor to you guys if you have any question. And then the main event is a drinks at the end, where we all can discuss and chat about how amazing Rhino and Grasshopper is in our day-to-day lives. Without any further ado, I would like to welcome Miriam to kick off the presentations. I'm sorry, that was actually me forgetting something. We have Carlos with us here as well, from Rhino in Barcelona. We will start with Carlos, actually. My bad. We'll go over a few new developments in Rhino 8 and a few upcoming stuff that I think we are all can't wait to hear about. Sorry. Carlos, please.
And today I'm not going to present Rhino 8 because actually it's in the market since a few months already. And I think in the last user group meeting, Luis Fraguada already talked about it. My presentation is more, well, on behalf of McNeil, we want to thank to all the people that have made it possible that Rhino exists since 25 years. And at the end, also, I will end with a petition. And don't worry, it's not about money. We are doing very well as a company. So last year, in October 98, Rhino 1 was released. That means that in October 2023, it was the 25th anniversary of Rhino. We have more than 500,000 users worldwide today in many different markets. And the company is still growing organically, but yeah, we see every day new examples of new markets and workflows and amazing projects, as we will see today. Last year it was hectic because we also organized a McNeil Global Developer Meeting in Barcelona with more than 100 commercial plugin developers, but also computational designers. Then in October, we had Rhino World, also in Barcelona, with around 300 people, McNeil staff from all the regions, from US, Asia, Japan, Latin America, Europe, all the regions, worldwide resellers, industry partners, and also key accounts. It's like a family. McNeil is a small company, but we have a very strong network of resellers and partners. And it's really amazing to see that we are still working with some partners and resellers since 25 years with the same people, and they are still very passionate about the product. We also organize many user meetings, same as here, but in other major cities in Europe, and we'll continue doing the same during the, next year, this year and next year. We've also organized many Rhino user and Food for Rhino webinars, and here I invite you, if you want to do a webinar with us, you have a nice project, a nice case study, or, for example, today with guys from Hive, we can also do a Food for Rhino webinar with you. I mean, this is open to everyone, being a user or a developer. And in October, we released Rhino 8. It has been amazing. During the last months, we've sold thousands of upgrades. I'm not going to talk today about what's new, but you have this page on our website. There is an evaluation version. I hope you have upgraded already. If not, please contact Simply Rhino. And yeah, we are still, the load of tech and sales support is still very high because people are still installing the new version and they forgot about the previous version, or they're finding some bugs, or there are some issues with the graphic cards. We are still fixing many things here, but I think it's going very well, and people, in general, the feedback is very good. Another milestone is that we have now more than 1,000 third-party apps on Food for Rhino. So thanks also to the community of developers. Many of these apps are free of charge. Some are commercial, but there is always a trial. And yeah, it's still growing. I'm amazed because I don't see the limit here. And yeah, again, Food for Rhino is free to use, so you can upload there. Now, not only your apps, Rhino or Grasshopper apps, also 3D models, resources, books, tutorials, anything. And we are working on a new version of Food for Rhino. There is a team in Barcelona doing Food for Rhino that hopefully will see the light during the next year. Luis Fraguada, who was here 3 months ago, is now the product manager. What else? Yeah. Besides all these third-party plugins, in the last years, being it with the inside technology or not, we are also trying that Rhino connects in a live way, in a live mode, with all other major software you are using. So there is Rhino inside Revit, there is a live connection with ArchiCAD, with Tekla, with TopSolid, with BricsCAD BIM, Sophistic, etc. So we are also working very closely with these partners, and we also try to attend their conferences, to work also together with their resellers, so that at the end our users that are also using their tools have it much easier to work with a solution. So this is also a big area, a key area at McNeil these days. And one more thing, I don't know if you have downloaded it already, but it's free. You can go to the Apple Store and download iRhino 3D. It's not only a viewer. The new version is also a scanner if you have a LiDAR sensor, if you have the iPhone or iPad Pro. And also, it has also augmented reality features. So I really recommend you to download it because it's free. And again, you can even scan a room, and later the geometry you get can be annotated automatically, and you can get the 3D model in Rhino and continue working in Rhino. And in future versions of iRhino 3D, we will also add some push-pull features. The new push-pull features you see now in Rhino, some of them will be also available on your iPad or on your iPhone. And now to my petition. Again, it's not about money. Well, I don't know if you know much about our company, about McNeil, but McNeil is a private held company. That means that all the income comes from the users, there are no outside investors. This is good also because we work for our customers only, for the users. I mean, we don't work for the stock exchange or for equity companies, etc. Also, most of the staff at McNeil are developers or tech support or training people. Our marketing is very limited. I mean, our marketing is these events, our blog, our webinars, etc. But we don't spend money on magazines, on advertisement, we don't sponsor very big events. I mean, we go there and we help with workshops if they want, but we try to keep the marketing expenses really low because at the end we want to offer an affordable product. And here you are key because you help us a lot with the development and with the support. I mean, our aim is also that every Rhino user is a trainer and a support guy or woman, well, or binary. So that you are part of the family, part of the development team, part of the support team. I think it's a very nice reciprocal relationship. But we need your feedback. We need your feedback every day. For example, now I was talking to Luca Viselli, and he was telling me now that he found something strange when he's rotating a model in SAP-D, etc. and so on. And I told him, but did you report it on the forum or did you tell us already? No. Okay, then it's impossible for us to fix that. So our petition, my petition, and the petition of McNeil is that please use our forum. Don't be shy. Pester us as much as you want, but we need your feedback. We need to know what are the bottlenecks in your workflow, what is working well or should work better, what are the trends, which other tools you would like to connect with Rhino, and so on. So the petition is that please use much more our forum or write us directly. And yeah, that's all. That was my brief presentation. Thanks again to the AJ for the organization and hosting of the event and to Simply Rhino. And I will be here during the conference. And also, Paul told me, no, don't tell that because maybe you will be very busy. But tomorrow I'm in London. I don't have a fixed schedule. If there is any company, individual, student, whatever here that wants to talk to me about anything about McNeil or Rhino, I'm not a computational design expert, but I know Rhino pretty well. And I know, of course, we can also talk about education in Rhino, what are the resources there, or how can we help startups or developers, anything. Feel free to contact me, to tell me, and I'll try my best to meet with you. So thank you.
Thanks everyone. Thanks Milad, Elif. Thanks Paul. Thanks Stephanie for organizing it, and thanks Lorenzo for the hot potato. Lorenzo just has a 6 days old bundle of joy, so he recruited me to be here tonight. Hope it's not going to be too boring, but you're stuck with me. I decided to divide the presentation into two parts. In the first part, I'm going to talk about computational engineering at ELC. And on the second part, I decided to bring the old logo back. I will bring some food for thought, not for Rhino. Where's Carlos? What I decided to do is to be open and talk about things that we used to go to the pub and discuss and have the computer and be vulnerable. So this is us having fun, being vulnerable, and actually designing great buildings. Actually, O'Callaghan is very famous for structural glass. We have designed some of the most incredible structures across the globe. And we have a very knowledgeable facade engineering team, as well as a very creative structural engineering team focusing on other materials as well, particularly timber. We have recently added another service, facades, access, and maintenance, to our portfolio of services. We are a little bit younger than Rhino. We are actually 20 years old, just turning 20 years old. And to give you a sense of scale, there are 155 of us, spread across the globe, ranging from Sydney, Hong Kong, Delhi, Milan, Paris, New York, and LA, and of course, London and Manchester. And within these main teams, glass engineering, facade engineering, and structural engineering, we have 3 horizontal teams that together make us very special. I will talk this evening about our computational engineering team. There are 30 of us, and you might be asking, you are 155, how come you have 30 computational engineers? The reason why is because we are rolling on a decentralized manner. We have computational design leads in every single of our international offices. And every group here in London, glass facades and structures, has a lead. And we have several champions working in their own specialisms, as well as people who are actually computational designers per se. And because of our scale, we really need to focus on things that we are very passionate about. And I will mention some of them now. Integration is one of them. I think computational engineering, computational design per se, is the big weaving thread amongst us, architects, engineers, designers in general. And we have been working on a crescendo of projects providing the 3 services together. As I move, it's been 1 year and something that I am in engineering now, I understand how interoperability is important, because simulation is usually not done in Rhino, it's done somewhere else, and we've been focusing on connecting all these other platforms. We've been working very closely with our sustainability team, empowering them with several tools. Some tools go from early design stages when things are still unsettled in Rhino and Grasshopper. When things start solidifying, we move on to Revit and all these tools, tracking embodied carbon and whatnot. Recently, we have developed a new tool for the facades team as well, accounting for embodied carbon and new values. Of course, by our tradition in advanced modeling for glass has brought us to a plethora of tools, particularly focusing on parametric advanced FEM analysis, and advanced manufacturing for glass and more complex materials. And of course, computational design, we provide tools and increase the services of the company as a whole for our clients, for our demands. And the facade engineering team has a wonderful team that's looking at building physics and the matters of environmental design and operational carbon and whatnot. And of course, computational engineering, computational design comes hands on hands with computational research and innovation. And here are 3 projects that I picked for tonight. We are working with topology optimization as a means, not as an end, integrating it to more traditional design engineering workflows. We have been researching about advanced robotic for additive manufacturing of facades, as well as finding forms for the most peculiar load cases. So this is a little bit about us. So moving on to the Grasshopper user meeting. I decided to connect the dots looking back, and for my birthday I got, as a gift from 2 of my friends without speaking with each other, a book. And I thought I may as well read it. Is the Containment Manifesto, I must call, from Mustafa. I'll also go back to 2016 for Pedro Domingos, the master algorithm, and to the mid-80s, Donald Schoen's The Reflective Practitioner. So the journey through these eyes is much easier because I can just access my memory, but I am keen to listen to hear about your own journeys on computational design. So here we are in the morning in 1997, rushing to the office to get a computer that had Windows installed to pick up a license of AutoCAD 12. Otherwise, you would be left with the machines that only had 11 on DOS. So AutoCAD 11 as well as AutoCAD 12 had 3D, and it was very clunky and it was very painful. And so I moved to another intern in a different office, and it had this thing called Rhino. And I know people on the forum have been celebrating Rhino, and I don't have the box because I only had Rhino in the office. People have been posting the manual and whatnot. So I believe my machine had Rhino too. The computers for the more senior architects had Rhino 3 installed. And so taking a moment to wish happy birthday, Rhino. And so coming back to the reflective practitioner, in this computer, I was helping on the design of an airport terminal. And right next to the computer, there was a drawing desk with all the technology of the parallel rule and whatnot. And one day, the lead architect decided to change the whole of the design, and we spent nights and nights redrawing everything, the classical problem. And so I looked at that drawing table, and I was like, oh my God, we're just mimicking what we do in the drawing table here because we had to draw everything again. And now we have this amazing technology. And so it took me back to uni, to the Department of Information Technology, to see whether I could find some parallels between other applications to do things a little bit more smart. And I was very lucky because where I come from has a huge tradition in the design, invention, innovation of aircraft. And actually training for that particular design is done in the city that I was brought up. And so I embarked in this journey with a bunch of aerospace engineers and an architectural intern. They probably were asking, what's she doing there? And they were using something called CATIA. And CATIA was quite interesting because it had something called the sketcher, right? So the sketcher, you basically design your parametric constraints in 2D. And you flip back to something called the CAD part, where you actually have your part, and this part is an actual file in the computer. And the combination of the several parts forms something called the CAD, the assembly, or the CAD product. And if you make changes to one, they cascade onto the other, and everything is amazing and parametric, and no more drawing over and over again. And the problem was that there was no architectural office that could afford a license of this thing. And it was only at the uni lab that I could find a license to use it. And so I went on to some darker ages using 3D Max, but the 3D Max had something quite interesting, procedural. You have the modifier stack now, right? So you make modifications in the beginning of the tree, and they cascade down all the way to the end, and so somewhat saving some time and actually inheriting things and making things a little smarter. But things in my life were heading to the UK, and I could feel that I was going to end up in London. And so I started making a research on what CAD software do they use in London. And I realized that in the UK, we drink a lot of tea. So you had to use something that you can hold the cuppa with one hand and click away with the other. And so it was MicroStation. And on top of MicroStation, there was this thing called generative components. GC had something interesting called the symbolic tree. So you would drop things on your parametric model, and a node would appear in the symbolic tree. And the versions that I used, you couldn't do much unless move the nodes around when they popped on top of each other. But you could see the parent-child relationship on a parametric model. And it also was somewhat procedural because it had this thing called the transaction file, where you could play transaction by transaction, sometimes disable some of the transactions, sometimes enable some others. So it was quite powerful, as it was painful. But it has some sort of rigidity to it. We were designing the wings of Zayed National Museum in Abu Dhabi, in my previous home, and we found a big problem, a deal-breaker problem. And unfortunately, we had to start modeling in other platforms. And of course, Rhino was one of them, and it was the first time I encountered this. Freedom! You have a canvas. And you can pop everything in the canvas. You have to really think responsibly about a parametric model, but you can think creatively about it at the same time. And and we would report issues to David in the morning, and David would release another version in the afternoon. And it was an incredible communication. And this is where I felt embraced by the community of Rhino and the forum and whatnot. And that's why we're still here tonight, I suppose. But there's something to talk about here. Now, the matter of fact that everybody's contributing to the thing, and we have everyone finishes their PhD thesis and pops another plugin over there, and now we have everything and everywhere, because now everybody's connecting everything and is connecting one platform to the other and to the next and everything. And every single company, startup that comes here comes with a promise of bringing us together. And there are so many options that even in the same office, we have different workflows. And what comes with the promise of bringing us together, isn't it taking us apart? Just my food for thought for the first one. So, and now there's even a bigger problem, because now we have everything everywhere and we have AI, right? So I want to talk a little bit about Domingo's text. So Domingos classifies these groups into 5 tribes. So we have the tribe that simulates what happens in the brain. We have the tribe that talks about evolution. We have the logistic tribe. We have the probabilistic tribe, and we have the analogizers. And I'm pretty sure that a lot of people in this room have written one of the algorithms for a particular tribe without even knowing which tribe they belong, kind of in the beginning, but some people with more knowledge about it. But this is the situation that we have at the moment. And Pedro talks about something called representation, evaluation, and optimization. These 3 aspects. What does he mean about it? So reflective computational designer. Representation is the AA model itself, right? Evaluation is the questioning of what AI model structure is appropriate to the kind of data I have and to the kind of data that I want to output, right? And the third thing is the optimization. So don't take things for granted. Are there other algorithms that do exactly the same thing in a much more efficient manner? So, so we have a big, and this thing is huge, and now we have everything everywhere. We have AI, and we have a big dilemma. I mean, now I am back to Suleiman's text, and he talks about catastrophe, he talks about surveillance state, and he talks about containment. And he mentions in his book 10 measures, and one of them is called the bottlenecks in technology. I'm not going to mention details now because I don't have time. But anyways, so fasting forward a little bit, talking about this project, I had a much smaller challenge some time ago in my previous home. And the reasons why I'm talking about this project is because a really large practice was in a transition between MicroStation and Revit. And we were in this interim between the two. And nevertheless, we had to deliver projects. And we had designed the whole thing in Rhino and Grasshopper anyway. So we decided we may as well document it in Rhino and Grasshopper. And at the time, there wasn't Make2D, there wasn't so many readers and writers, and so we developed so many tools for this project that it was incredible. But the thing was huge, so we had to bring a big challenge into smaller chunks, and we were talking about dividing this project into different files, and each of the files would be interconnected, and the very person who actually validated a document that was called the geometry method statement. So, coined by the irreplaceable Hugh Whitehead, the geometry method statement was meant to be a piece of document that is software agnostic. So people in manufacturing, people in consultancy would pick up this document and model the whole thing in their own way. And but to do so, we had to document it in a way. And in the beginning of this document, there was something called the diagram of dependencies. And here I make an analogy with UML models, particularly the class diagram, and even the peculiarity to the composition links. which basically divides a package into classes and creates the interdependencies between classes. And the beauty of this is that you can identify parent-child relationships, and you can create checks, and you can create bottlenecks to check whether the AI is not hallucinating, whether the simulation by the engineer came correctly, where things to manufacture are going in the right direction. And I think the diagram of dependencies, it's quite an important part of the process. And I just want to finish this with the happy moment when I saw David in the workshop last year, showing these two things, the shouter and the listener, and indeed the diagram of dependencies. And now we have dependencies between files, and we can establish much easier checkpoints. And in this world of interoperability, this has a huge key role. So I'll leave it there. Thank you.
All right. Good evening, everyone. My name is Jonathan Wong. I'm joined here today with Pooja Bhagat. We're recent MR graduates of the EmTech program. So we'd like to thank Alif, Malad, Simply Rhino for organizing this event and inviting us to speak, because we're really excited for this opportunity to introduce to all of you our newly developed Grasshopper plugin, which we've entitled Hive, which is a socially driven pedestrian simulation. So tonight we'll touch on some of the background, the history that really led us to develop Hive before going into the exact details of what Hive can do, how it functions. And then we'll showcase a few example applications that we used during our time at EmTech, as well as share a few updates, things we're working on to release in the future. So the development of Hive emerged from our MArch thesis, which we entitled the P2 Tower at EmTech. So we were investigating the discontinuity between the temporality of people's sociability in relationship to the permanence of the spaces they inhabited. So specifically, we were investigating the complex urban environment within Hong Kong, and we designed a new housing tower and urban network system that was able to meet the density needs of the city while also facilitating continuous spatial changes to match the changing needs of people over time. So that was really the overall goal and framework of our thesis. So the design of the P2 tower was really driven by 4 interwoven narratives, which followed this changing needs of a family unit over time. So through these narratives, the P2 tower explored how shifting social interactions could facilitate spatial changes. And this flexibility was really achieved by employing a series of computational tools, such as multi-objective optimization or biomimetic principles. So by using social interactions as a driver for design, we were able to distribute public and private spaces vertically throughout a housing tower. And then our thesis also looked at this idea of sociability at varying scales, developing a series of pedestrian pathways and multimodal corridors connecting parts of Hong Kong throughout the city. So throughout this thesis, we really aimed to address the dual issues of densification and ever-changing sociability by designing this interplay between public and private spaces that always transformed with its residents over time. So in order to achieve this, clearly defining, let's play this, okay. Clearly defining these terms, public and private, were really critical to the development of our thesis. So in an architectural setting, we were looking at these ideas in terms of sociability, or how likely people are to engage with one another. So based upon this notion and existing research, we developed a system which enables us to quantify the system of sociability within a space, particularly as it changes. And this enabled us to adapt a space to meet people's changing needs over time. The system was based on a series of measurable parameters within an architect's scope. And here you can see how some of those are calculated or measured at the scale of a building. But it could also be adapted to smaller scales or larger scales as needed. So this sociability spectrum, as we called it, really was the driving force behind our thesis and later underpinned the development of Hive, as it enabled us to quantify those social interactions, the sociability of the context as a driver for design. So as we employed the sociability spectrum within our thesis, it was necessary to understand quantify and really leverage these social interactions in order to design. However, we found that there weren't really many tools out there which sufficiently met our project's needs. A lot of the existing pedestrian simulations or tools that existed lacked any consideration for social behaviors. And beyond that, they were often only used as post-analysis tools rather than generative ones.
So knowing this, we developed Hive, which stands for Human Interaction Visualization Engine. Hive is a pedestrian simulation plugin for Grasshopper, which leverages human interactions for generative architectural design. To understand why Hive is particularly unique, let's take a look at traditional pedestrian simulations. Most simulations begin with a series of constructors, some versions of agents, environments, and destinations. These elements are then initialized and employed within the algorithm's main engine to actually simulate the pedestrian behavior. Typically, these behaviors will be to travel to certain destinations and stop at places along the way. And finally, the most important part of simulations is output data, which will typically relate to some sort of agent movement and some sort of visualization in heat map form. And Hive implements all of these base functionalities, but introduces a third social interaction driver of design. This functionality is not only applied to individual agents who have tailored social abilities and requirements, but it's also integrated across the entire environment as well, providing the ability to define global social parameters and seasonal adjustments. Hive facilitates these social behaviors on multiple scales using geometry and data which are particularly tailored to that specific domain. And beyond that, the data coming out of Hive can be used as a generative tool in a feedback loop to continuously improve the given design. So in doing so, Hive can empower the designers to leverage social interactions as a driver of design, which in a way humanizes the computational design process. Now let's take a look at the actual functionality of these social interactions. As two agents come in close proximity with one another, their individual social levels are tested. And the closer their values are to each other, the more likely they are to interact. And additionally, those with higher social levels are more likely to engage than those with lower social settings. This probability is guided by global socialization levels, which determines the difficulty factor for that social interaction to occur. And of course, a small randomness factor is introduced to kind of mimic real-world behavior. And we've adapted this kind of social behavior for 3 specific simulations. We have a network-based, cellular autonoma, and a physics-based simulation. At the moment, we fully developed the first 2 methods, and we're in the process of developing that third one. And as you can see, each method follows about the same logic, but employs specific geometries and parameters and data types, which are specifically relevant to those scales. And in doing so, Hive can leverage those sociability behaviors across different domains to cater towards multiple use cases and design scenarios. Now let's take a closer look at each of those developed methods to see Hive's specific functionality. The network-based simulation is Hive's largest simulation engine, where agents can move and interact along specified network paths, such as, at such a large scale, agents and destinations are defined as types rather than as individuals. And algorithms can then introduce movement and socialization based on agent journey requirements and access parameters. And once a simulation is complete, the data coming out of Hive can facilitate multiple types of analyses and iterative design processes. The most versatile part of this is the data output, which is a social behavior log. This feature produces a running history of all agent movements and their behavior states at every iteration. And with this data, designers can easily create global metrics for their networks, such as constructing socialization heat maps or comparing network efficiency to social interactions. And designers can even draw individual connections between multiple agents across key moments during the simulation, which kind of helps them facilitate more detailed design decisions. To run a network-based simulation, users can abstract their city-scale designs into a series of network curves, which represent all possible paths an agent can follow. Along with that, the destination data and pedestrian definitions are required. Agents can then move driven by their shortest path algorithms and by their local and global sociability parameters. Line-based algorithms, this type of line-based algorithm is particularly useful to help you simplify complex design scenarios into relationships and connections. And in doing so, this kind of network-based simulation is best suited for understanding mass movements and community behaviors. Using this information, the algorithm can simulate pedestrian behaviors across the whole network. Once the simulation is finished, Hive's output data can be used to facilitate multiple types of analyses, which are geared towards different design goals. In the first example, here we can compare several different types of networks to one another. This may be useful when you're considering multiple design options for the same site, or perhaps a staged development of a specific design. And in this specific example here, we employed Hive during our thesis project as a tool to select the best performing network from a series of optimized design options. Here you can actually see that all three were supposed to be highly performative individuals from our previous objectives, but when we integrated Hive's social behavior functionality, we can see that they're actually not the same. They're actually very incomparable. So we can see that how Hive's social functionality adds additional benchmarks, which helps, that's fine. Sorry, everyone. We can see how Hive's additional parameters help benchmark designers to specifically tailor their designs to human interaction as a driver of that design. In the second example, we can compare the same network across multiple settings. This may be useful when you're changing community dynamics or if you want to simulate a social adaptation over time. This example is also from our thesis project, and in this case, we used Hive to understand the effects of variable social behavior on the very simplified networks. And as you can see, a change in agent behavior can drastically change the landscape of agent movement. This is showcased through the increase of density across the network, which could insinuate a natural gathering behavior for community members. Using the output data from Hive, designers can understand how pedestrian behaviors might differ over time and space, and therefore begin to adapt their designs continuously throughout time. And this can help us in a generative design process where you can run one Hive simulation, understand the output data, and continue to optimize your designs.
So alongside the network-based simulation, we also have the cellular autonomous simulation method, which we can take a look at now. So as compared to the network-based simulation, specific destinations or paths of movement for the agents are not specified as inputs. Instead, this algorithm moves agents based upon their specified social levels in respect to other agents, surrounding program, the context, with a touch of randomness as well. And through such a method, the simulation showcases how programmatic arrangements really can encourage opportunities for social interaction within that space, or how agents may move within a space. So specifically, the cellular autonomous simulation operates on a medium scale scenario by introducing spatial characteristics to the agents, the program, and the context. Agents are defined by a sociability score and a prevalence within the simulation. Program spaces are randomly distributed throughout the environment. Combined with the sociability of the existing context, this program helps make up the overall environment of the simulation and influence the way in which agents move according to their proximity. So the agent's movements are determined using a 9-square grid where cells adjacent to the agent influence the probability that it moves in a particular direction. So as Pooja demonstrated before, these probabilities are determined by the proximity and the relationship between the sociability score and whatever exists within that adjacent cell. So agents will either move towards desired program spaces, towards agents of similar sociability, or away from agents or program spaces that may vastly differ from their sociabilities. And unlike the network-based simulation, the randomness that is inherent in a cellular autonomous simulation affords the opportunity to really account for the inherent randomness of that people may behave in a space, as well as generatively explore different design options and scenarios that may occur. So as you can see here in the simulation, the location of those programs in the sort of the southern end of the environment really drove people, we can see from the simulation that really drove people to move within that open space between it. And from this information, we could iteratively add more program later, or subtract program in other places, depending on your design goals, whether it's to distribute people throughout the space or concentrate people in large areas. So I mentioned earlier our thesis, we developed a series of multimodal corridors which connected parts of Hong Kong. So we employed the cellular autonomous simulation method here as a first case test scenario to design context-specific program arrangements along these corridors, which was able to respond to different urban scenarios by weighting the program and the context based upon open source data we were able to obtain, as well as using that sociability spectrum I introduced earlier. So through the simulation, we were able to understand how a particular program arrangement along this one site was not necessarily conducive to social interactions or moving people through the space. So you see in that image there, there's a high concentration of people spending time towards the, again, southern end of that space. By utilizing that output data that we were able to get from Hive, we adjusted the input parameters of the programmatic arrangements to simulate, in our case, how this space might adapt over time, not necessarily an initial case scenario. And the resultant design showed an improvement across the metrics through when we analyzed it with Hive again. And iterating that on a third time, we were able to generatively develop a well-suited programmatic arrangement for this specific section of the multimodal corridor, which performed well in terms of social interactions and programmatic use, and specifically responded to the urban context it was in. And you can see how we could continuously use this methodology and this system to respond to changes in the space over time. So those were the two methods that we have currently developed, and here's sort of a sneak peek of what we have in the works of the third methodology of pedestrian simulation that we're working on is physics-based simulation, which again is driven by the ways in which people, these agents may interact and move within the space, but operating on a much smaller scale and in 3 dimensions. Other things we're working on adding into Hive are things like agent recognition of repetition as they interact in the space, group movement of these agents, clustering in spaces, or how their movements might differ when they're no longer individuals, and also looking at how can these agents' sociability change over time, or how and in what ways that might affect the simulation. So thank you very much for having us tonight, and if you have any questions or comments, feel free to reach out. We'd love to hear your feedback using it, or any features you would like to see introduced into the pedestrian simulation. And I see people with their phones out already, but Hive is available for download on Food for Rhino, so if you scan that QR code, it'll take you right to that page where you can download and play around. There are a few example files in there that you can use. Thank you.
Hi, I'm Olga. Thank you for having me. I suppose my topic is a bit unusual, as well as my general kind of, well, a bit less unusual than it used to be, but obviously I'm coming from a product design background. It all started here as a person who is a product designer, but also interested in computational design. I came to EmTech over 10 years ago now, so I'm quite old. And I think at the time when I graduated, it was quite hard for me to find applications for computational design that are functional and not decorative, a little less so today. Until I met the founder, of a person called Dr. Dan Plan, who is the founder of the company where I work today, which is called Rion Labs, which I'll tell about. So I'm the head of design at Rion Labs, and I also teach at Imperial's Dyson School of Design Engineering. So I suppose the purpose of today is to show a bit what we do with Grasshopper and kind of our current workflows. But to put things in context, because I don't think it's quite straightforward, ultimately what the company does, it has a technology, which is effectively metamaterials that enhance, basically designed with computational design, and it's this technology that's applied in sports engineering. It's an ingredient brand. So we effectively, like Gore-Tex, so we partner with companies like Adidas, for example, and enhance products. Technology currently comes in 2 formats, which is 3D injection molded and in film, and I'll show you the case studies. But I will also explain first a bit more about what the technology, because I think it's important to understand technology, and that's basically what Dan had when I met him, is effectively this reactive polymer, which is strain rate sensitive polymer. It means, obviously, it responds to forces depending on the speed and loading you apply to it. So you can imagine if it's a molded stack of material, the faster and harder you hit it, the stiffer it becomes. And also the same also applies in other types of energy. So if it's stretched, the faster you stretch it, the stiffer it becomes. So that's aspect one. The other aspect is where I suppose the video doesn't play, or maybe it does, maybe it doesn't. There you go, is the aspect of the geometries and computational design, because that is actually not just an added value, it actually amplifies what the base polymer does. So in the example, if I try to replay the video, you can see these kind of castle structures are designed to have a soft initial response, but obviously as the loading increases, they become stiffer. And you can see how that is useful in applications such as helmets, where you would have kind of a soft day-to-day use, but if you, God forbid, smash and crash, then material becomes stiffer and absorbs the impact better. So that's the essence, I suppose, of the technology. Then I'll show a couple of case studies of how we applied and how obviously Grasshopper and computational design come into play. But in the first example, what we do is kind of talk about a bit of body armor and protectors. So just if you're not sports enthusiast, normal or often body armor protectors are effectively a big stack of materials. You have maybe a plastic shell on the outside, so sort of scratching or surface, and you'll have a thick layer of, say, energy absorbing foam and a thinner layer of something that's more designed for comfort. So a lot of materials coming together to create this. The issue is, A, obviously you're using 3 different materials. That's not very good for the environment, and then generally not necessarily the kind of smartest way to do it. But also it treats the human body as if it's all just a single shape that doesn't actually have different shapes and different features. So it doesn't differentiate between where your bones are or where your soft tissue are and how you're actually going to use it. It's quite generic. And that was the first, basically, application that we did now over probably 7 years ago, where we said, well, let's just rethink that because we can do that a lot better. So we took a lot of body scans and tried to kind of identify. Obviously, it's quite repeatable where you identify, for example, the kind of closeness, the distance to the skin in terms of bones versus joints versus soft tissue. But if you try to also consider the variation in different population, or let's say predominant areas of impact or scrapping, so you start to add a lot of layers. And ultimately, and this you'll see that as a repeated theme, I think we use a lot of kind of creating our own analysis, creating heat maps from that analysis, and then using that to drive something in the design and geometry. So here, effectively, we interpolated all these maps to kind of create the boundary area and how that should differ, and then generate the geometry based on that. Now, there's obviously the very popular Voronoi, but in this case, I think it was particularly useful for us and still is useful for us because ultimately we utilize a quite irregular boundary and populated with cells according to quite a complex range of parameters. And basically, we utilize that boundary to the maximum so that you have there's no cell that is the same. Ultimately, each cell is individually tailored to that specific area that it's designed to protect. And there's a degree of other analysis we do. There's a lab. It's not Rion Labs. It's actually a lab in Battersea. But a lot of it comes from empirical test data, of course. So in here, this attempt, you can see us trying to map effectively body armor goes through rigorous testing standards where effectively you put it in between 2 metal anvils, drop it at different energies, and record, obviously, the transmitted force. So this is us trying to map that transmitted force and therefore what it should mean in terms of characteristic of geometries. And kind of the evolution of these parts, I suppose today you can see that in actual 3D. The injection molding process of it ultimately is 3D printed tools, but the injection molding is done the way it's traditionally done because the material is quite soft. You can imagine we have a degree of freedom in level undercuts we can pull out, but I wouldn't say it's unlimited. We do have one-off tools that are now door stoppers, but you can see here basically the variation in cells and kind of how the final parts tend to look, and some of our more different parts. But ultimate result is this kind of protectors, whether it's for motorcycling or other applications, tend to be both kind of a lot thinner than your average market ones, a lot more breathable, and a lot more lighter. And yeah, that makes it worthwhile, I suppose. Show you other types of workflow we do. It's quite similar, but I call it datifying the comfort. But it's a lot of the times the parameters we're trying to use or understand are not either well understood or not numbers. They're effectively human-centered design factors. So, of course, you can optimize a helmet or a body armor to be sort of as protective as possible, but there are aspects of it that are interconnected that are more subjective things. So for helmets, for example, they're a bit of the same, but if your helmet doesn't fit you well, it actually won't protect you well, just so you know. But and the way these products are made is quite traditional, at least in many cases it is. So for us to create our own set of rules where we can say, actually, if you give us all the 8 different sizes of helmets you do and kind of start taking scans or head forms from testing and trying to analyze in terms of the distance between the head and the inner surface of the helmet, trying to identify hotspots. But it also gives us a way of deciding where we can put our technology, because you can imagine it's an added bit. So it's what we call the stand of difference. And often the areas where you need it most is the areas where you have least space. But the whole point, I suppose, of working with companies from the start of the project is that you can kind of factor these things in advance. It's not always the case. A lot of the times, and that's, I suppose, part of the difficulty of being an ingredient brand. It will be, here's our product, we're not going to change it, but make it amazing by adding your technology. And that's quite difficult because you can, no matter what you do with Rion, you're adding material. So therefore, it's quite the trade-offs of having this kind of more intelligent material and more intelligent design kind of can sometimes disappear. But obviously, that's part of the workflows we use it also in terms of Grasshopper. Try to identify impact directions, which are normally in started. And obviously, in reality, you can fall in any angle, but you try to map the primary, but at the same time, identify where could be sort of possible pain points for the user. And therefore, as a result, what could be the design with the existing real estate, so to speak, because the footprint in real estate we work with is quite limited sometimes. The thing I wanted to mention, actually, I forgot to mention about the body armor earlier, but the geometry aspect of it is crucial because you would think that there's a linear relationship. If you take just a solid polymer and not design as a block versus one with geometries that the one with solid will perform more because there's more material in it. But in reality, the geometries enhance the way the polymer works. And there's also often, when we test, 20 different designs, you wouldn't see a relationship whereby more materials means better performance. And that's, I think, for me at least, one of my big aspirations when we achieve more with less material. Different case study. As I said, we do have applications in film. It all started before the previous Olympics. with the kind of looking, you see all these athletes running on your screen and you see this kind of muscle wobble. And it became this whole hypothesis that ultimately what happens there as you run and hit the ground, your muscles go out of plane and therefore that vibration is a wasted energy. So if you actually redirect that specific type of vibration, then you make more out of your own body and therefore become faster and better. A lot of study and research went into this. We then partnered with a couple of universities. We filed our own IP on this. It was quite a journey. From a computational design perspective, where it often lies is in this kind of a 3D, 2D, 3D process where we try to map the muscles and understand kind of where we want the technology, unwrap it on flat pattern of the garment, make a design and then wrap it back again. That's kind of the common workflow. And I'm supposed to show a bit more advanced progress of it, where we try to integrate also how people move or how, because ultimately compression garments need to be compressive to a certain level, but they cannot be over compressive. So considering how you flex. But yeah, this is kind of one of the more advanced designs. We like to present this to clients and to ourselves, but to a degree it's true as the design problem generates its own solution, because if you just let kind of all the parameters from the body to be the one driving the design, then surely the design is as pure as it could be. But the big sort of testimonial result for me personally is obviously to see athletes wearing it and actually doing better. I hope it's because of us, but if not, we'll still say. But yeah, recently in the last year since we launched it with Adidas, there's been quite a few medal winners. Just for your awareness, if you're, this is a game of marginal gains, so to speak. So 1% or 0.8% is literally the difference between being on the podium or not. So these kind of incremental changes and design aspects are quite important to them. Other aspects, and I am sorry if this makes anyone uncomfortable, but I suppose I'm quite used to think about the engineering behind sports bra. But this is actually one of the most increasingly studied areas, I think. And to a degree, still a lot of it is quite unknown. We started at the same time because ultimately for many years, and our CEO also spent many years at Marks and Spencer and knowing the kind of the sports bra industry well. The big issue is to make a very supportive bra, you have to make it very compressive, therefore it's uncomfortable. So there's a issue there. So the thought was that if we can introduce our technology with a dynamic effect whereby the more intense your activity, the more supportive it is, then it will be bingo. It's not that easy, but we're definitely closer to it today than we were. But from a kind of Grasshopper workflow perspective, our initial attempts were quite kind of taking it from the basics, so taking the motion capture analysis throughout a single gate and trying to really understand the motion, and it's quite complex, it's not a simple up and down. So try to kind of factor all that in and then sort of interpolate various displacement maps with the vector maps and trying to understand what that could mean for design. And on top of it being quite hard to understand the data, it's also quite hard to sometimes understand what your design, how your design affects the data. In my very naive first attempts, I think I also, we tried to do, basically I thought we could do live 3D scanning at the same time we do motion capture. It's probably there's a system that could do it, but I suppose with the facilities we had, obviously the motion, the 3D scanning is a lot slower, but still valuable data came out of it. Maybe with today, when I have a lot more time, I'll do something more valuable with it. But I suppose what the repeating theme here in terms of Grasshopper is we constantly try to create our own analysis tools with data that is not necessarily very accessible to us and through different aspects. Here as well, the idea of trying to create data from comfort. This is even harder to understand than helmets, but a lot of the time a bra could be just not the right size. So therefore, differentiating in the feedback what comes from fit limitation and what actually comes from technology is quite hard, or from design changes you could do. But what we often is just to create a lot of maps that drive the design. That could be either something we've just drawn and mapped ourselves, or trying to take sort of a whole list of subjective data we capture online or from users, and then turning that into a data. I think the thing that's particularly valuable to me is the aspect that we don't turn it into a sort of a computational mechanics exercise. And I think that's the one I'm really instilling in the team. The fact that the geometries are not designed to just perform, but they need to consider human central design in it, as well as design for manufacturing. So a typical project would probably have 5 to 10 different criteria mapped out completely differently in terms of ease of manufacturing. And even something like film that seems straightforward, there's a million different ways in which a company in Asia could peel it in different directions. And if you start optimizing just for that and just for zero waste of film, you'll probably just spend years just doing that, which is obviously in commercial deadlines is a bit tricky, but I think we're slowly getting there. But as well as human factors, just sometimes the things that would affect the design is, I don't know, constant areas of friction or skin, or people saying they didn't like the way their behind looked in it in the gym, or things like that. So it's all sometimes hard to sell it, but we try to quantify it effectively. And yeah, just to say, suppose example of the type of thing that ultimately come out of projects like this. There's obviously a lot in the pipeline that I'm not allowed to show. If you have more thought, I suppose, in the more informal part of this evening, I have my colleague Kami here with me, who also works at Rion, and a lot of the things you do is things he designed. I suppose the presentation wouldn't be complete before 2 other things, which is my teaching hat. So talking about my student work, I think since I started the module I hacked a module called Advanced Industrial Design to be about computational design, but they don't allow me to change the name. But students just always amaze me with their kind of insights and the things they try to do. It's quite a short model, and it's coming from a school that still relies a lot on tools like Fusion. It's quite hard for them at first to grasp Rhino and Grasshopper. But I think increasingly I see more and more students do it well. And a lot of them trying to link some human motion with an output in Grasshopper. So in this project, the student tried to link sort of a hand object for fidgeting, basically with the way your hand moves and fidgets, which was quite nice. I think to summarize my thoughts on this, we are definitely, and that's been discussed, in an area where almost a lot of the things we are trying to do, starting this kind of conversion where AI can shorten some aspects for us. But in the early steps of introducing things like Mid-Journey to the students, there's fairly good use in terms of kind of quick renders or initial ideations. Probably the admin system were a bit challenged by how you pay them, but generally I think it's quite promising, and I'm sure the day where we use it to things like prompt to get a code to something are very close, if not here already. It says questions, but I know they come in the end, so I think that's pretty much it.
Good evening, everyone. This is the last presentation of this evening. My name is Elif Erdene. I'm joined by Minat Shokatbaksh. We are the co-directors of EmTech. We would like to thank again Simply Rhino for enabling us to host this event at the AA. This was one of our aspirations for the past several years, which was to be, able to host one of these events. So we will be talking about a specific project, which is focused on a very specific computational and physical experimentation workflow. Before we get into that, we would just like to kind of show you a very kind of short summary, let's say, of EmTech. So for more than kind of, let's say, 20 years in EmTech, we have been exploring different lightweight material systems, and ultimately it's all about, let's say, experimentation, and it's all about the research process. We've been experimenting with novel design processes, computational methodologies, building systems, different material systems, so on and so forth. And all of our, let's say, computational tools and techniques and workflows are calibrated from physical experiments. So you're seeing here kind of various, let's say, different experimental projects over the 2 decades. We do believe that it is impossible to build on knowledge from only one project. So in each project, we focus on a specific let's say, computational workflow, computational pipeline, which is coupled to the physical experimentation process as well. A very important part of this process is actually the studio and the what we call the atelier tradition, and that is really about the human aspect. So we like to work collectively in studio with our students and develop these kind of various, let's say, computational workflows that are coupled to physical experimentation.
I mean, in EmTech, we have a long history of building, and one of the integral parts of this build projects is understanding how to transfer information between computer and a real physical world. Of course, there are a lot of pipelines that we utilize in a studio, but one of the most important of these pipelines is Rhino and Grasshopper for both ease of use and its universality. One of these projects are the manifestation of these generative pipelines that we test in our studio. They are realized either through industry-led projects that are sponsored by industry partners from Bureau Happold, Arab, to multiple different partners throughout the last 2 decades, or they are manifested in our thesis work of our students. Again, through which one of the integral parts is to bridge the gap between how material behaves physically versus when we simulate that digitally in computer. These are example works of thesis works in EmTech, collaborations that were done with other institutions and other industry partners. This particular one was done with ETH a couple of years ago, more than a couple of years ago. As you can see, EmTech had a long history of interest in thin plywood sheets and how to design and fabricate performative structures as lightweight as possible. And one of the key areas to come up with such design ideas is to first and foremost understand how they behave without prior to their built-up process. And this link is facilitated through the computational pipelines that we explore, we invent, and we establish here in EmTech.
So considering our history in working with lightweight materials, we have been recently more interested in biodegradable materials. And part of our research, so we also conduct an international workshop, which is called the D-Lab Visiting School, that takes place in London every summer for 3 weeks. This is a workshop that is open to architect students around the world, and our kind of research themes between EmTech and D-Lab kind of correlate with each other. So during this past cycle of the workshop, we worked with rattan canes. As you might know, it's a renewable and biodegradable resource, and we were focused on creating a lightweight structure through the bundling of rattan canes. Why were we interested in this? Because rattan cane on its own is obviously a very flexible, very flimsy material, but through its bundling and twisting, we can create more stiff, let's say, objects or structural components. So that was the initial research idea, and as in every kind of cycle of the workshop, we're interested in integrating generative design, material computation, large-scale fabrication, robotic fabrication as well. So we are going to kind of go into this research agenda, which now we are actually developing further in EmTech Studio. So as you might be aware, evolution favors the use of fiber-like, let's say, or fiber-based structures in complex living organisms. Many of these fiber-based arrangements involve the alignment of long, stiff, or perhaps sometimes not stiff members or fibers in parallel formations in multiple layers. So that brings in the idea of bundling and bundling in several hierarchies. And these material systems, rather than being physically connected, they are usually embedded in a matrix. And in our case, we did not have a matrix, but we have been working with friction-based material systems. So friction replaces the matrix in our research agenda. And again, fiber-based structures obviously have been practiced in human construction for centuries, both in vernacular practices as well as contemporary practices and more kind of experimental practices. And the materials have ranged, from, let's say, bamboo to other kinds of rods and reeds and willow canes and rattan canes and so on and so forth. And actually, this research has, in terms of the kind of focus on this research, some of our students have been experimenting in EmTech as well. So this is one of the recently, let's say, concluded Master of Architecture dissertations from 2022 by Maxence Florence, Louis Bossoms, and Rodrigo. And their focus was on coming up with a, let's say, multi-scalar design methodology to create a dwelling system in the Yucatan Peninsula. So they mainly work with bamboo as a material system and how bamboo can be bundled in different ways to create structural configurations, which we will kind of jump into this in the final kind of slides of the presentation. To contextualize the research. Another kind of interesting, let's say, reference for us was obviously we investigated academic precedents, research-based precedents as well. And the kind of gap that we identified, we could say, was how could we further explore stability through geometrical and material investigation by using canes? And how can we create some kind of, let's say, structural performance without the need of the structure being supported by an external framework? So these were our main considerations: to create a stable structure that is made from very lightweight canes that can be bundled and twisted together, and that has a certain structural capacity. And so given obviously what we know about materials and their properties, our main focus was what if we could design structures that actually take advantage of banding, making it an active part of the design process. So that obviously takes us to banding active structures. So that was the main interest. And of course, a very important structural principle we paid attention to is that stiffness of objects is not the same thing as stiffness of materials. So materials that are inherently, very flexible and stiff can be brought together with certain geometrical principles to create objects or structures that have stiffness.
To build on top of this very important principles and the fact that we were working with long, slender elements, in this case, were rattan canes, there were two important forces that we had to master when dealing with this material. One of them, axial stiffness, and the other one is bending stiffness. And basically, Elastica provides a more, there are three principles of curvatures that could be simulating the behavior of the material in a physical world when dealing with long, slender elements: circular curves, arcs, catenary curves, and elastica curves. Within these three principal curves, we started to experimenting of how these curves could be achieved with our material that we were working with. Since this was a part of the workshop, the brief was given to our students to experiment with long, slender elements, amongst which were also the plywood sheets, to better understand how these physical behaviors could be actually be understood and simulated in the computer and digital workflows. Building on top of this, there was an important principle that we wanted to explore, and it was bringing layers of materials together. This is a very important equation, and working with different layers. However, this was something that we started with, but we wanted to push it further, and removal of adhesive when dealing with different layers. Hence, we started to be thinking and working with what other ways could be possibly implemented to bring these long, slender elements and create variation and different bending behavior in relation to those very thin elements. In this particular case, we have the rod, of course, with a larger diameter might have a better performance dealing with bending forces, but the bundled rods allows for flexibility to create curvatures of various types. This was something that we wanted to explore in this context and research that we explored in the summer. These are the images of rattan canes that we acquired for this workshop. And the very first thing that we wanted to do, actually, to test our physical and digital workflows. So we created a real life physics and kangaroo simulation. I mean, for those of you who are familiar with Kangaroo plugin, fantastic plugin in Grasshopper, but we had to make sure that the pipeline and the workflow that we're exploring in Grasshopper can actually be correlating to what we get in real life. And this is what we try to actually understand, whether or not the Kangaroo simulation or the physics simulation that we have at our hand can be almost, not exactly, similar to the real life events that could possibly happen. This is me being happy that, oh yes, it's happened. One of these, alongside these processes, we were also experimenting with how to use the accuracy of robotic arms when bundling these canes. And these are the examples of different thickness, different ways of which we were bundling these rods together to create bundled elements. And these are, our students are laughing right now. One of the main and key areas of these physical experimentation is to understand where things fail. And this is the recent video, I should say, but we did the same thing back in summer. And we tested of how far we can twist these with robots and how far we can bend them before they fail. These are one of the important physical tests that could eventually help us to calibrate and to come up with a digital workflow that could actually be used and meaningfully tested. I mean, this research was part of the workshop, and like any other research that we conduct, we always start with small-scale tabletop models to have a very principal and foundational understanding of how material works. through which there were results of these physical tabletop models that were fabricated by our students. And they are all informative for us in the process of how to transfer this information back to computer.
So that process, all that student work, all the physical experimentation that we did resulted in, actually, can we start this again? Resulted in a very kind of basic, let's say, component morphology, which is this, that is prone to stretching in certain directions. So then we decided to insert the blue circular elements that you see that act as stabilizers. So those circular elements would actually enable the kind of stiffness of the component itself. And then obviously then there's the issue of the rotation on the component scale itself. So then we started looking into ways of aggregation, both horizontally and vertically, this component morphology system. Having said that, this component morphology is the result of a couple of weeks of research, and right now our students in EmTech are developing this morphology further to create a more kind of, let's say, spatial aggregation logic. This kind of summarizes our kind of entire, let's say, computational and physical-based workflow. So, as Milad mentioned, we started with these kind of very basic initial physical experiments, trying to understand if the physical experiment is actually calibrated to the kangaroo simulation. And correlating those two, and at the same time creating the material load testing. One of the key ambitions of these physical and digital simulations was to extract a Young's modulus that we could use for structural simulations. Now, obviously, in research and in academic papers, you can come across different kinds of Young's moduli for different species of rattan. But because rattan is a natural biodegradable material, sometimes there are kind of slight changes to those Young's modulus. And we needed to ensure that we were working with a value that is as precise as possible. So for that reason, we use multi-objective optimization, which Milad will talk about in a bit, to calibrate a coefficient that can be used in accordance with the Young's modulus. Then, so those studies in the local scale then fed into the regional scale, iterative finite element analysis, where we tested aggregations of these morphologies, both horizontally and vertically, and understand their structural behavior, which then led to the generation of our global morphology at the end of that, let's say, 2-week stage. Then it was about the modeling of the joinery system and the base modules as well, the base connectors. And both, coming from the physical prototyping in the beginning as well as the joinery modeling. Then we went into the robotic fabrication stage, which was focused on 3D printing with recycled pellets as well as bundling of our, let's say, morphologies, and then going into the assembly stage.
One of the issues that we faced, we said to ourselves, okay, we got the Young modulus, and then we can simulate what we could build in a Rhino and Grasshopper. But unfortunately, that was not the case, because first, these rattan canes reeds were extremely flexible and unpredictable. And when we exactly followed the step-by-step process of building, bending, and bundling them with the computer and the physical world, we noticed a massive difference. And the difference that we needed to overcome in order to go to the production pipeline. So one of the key things that we did in this phase was come up with a series of coefficients to be included in the physics simulation to make sure what we simulate with Kangaroo and Grasshopper is as close as possible to what we get in real life. And hence we did a series of multi-objective optimization with policy, coming up with a series of numbers and coefficients that could possibly be introduced to our pipeline in order to create what we wanted to create physically.
So then we use the resulting coefficients in our structural simulation. So first we start with testing two types of modules. Again, as I have mentioned earlier, the module kind of geometry and morphology is currently in development. At that time, we wanted to test two different modules with two different kind of stiffness values. And we started with testing the toppling behavior of single modules in Karamba in eigenmodes, basically. And then we went on to kind of analyzing different aggregations of modules, applying both gravity laws as well as point laws, modeling the joinery, so on and so forth, and testing basically what happens as we aggregate these modules both horizontally and vertically. So this essentially kind of sums up the entire process. We start with a very kind of simple, let's say, component geometry, which is strengthened by those circular elements, and everything is obviously bundled together. And then these components are aggregated in different rotations. So, I mean, this is also important to highlight for the structure analysis. They have different axes of rotations, so that also adds to their stability when they all come together, right? And the final morphology that we get at the end of this stage, I mean, the component morphology, we thought of just testing this as a demonstrator, just to build a wall, basically. We said, let's just try to build a wall first with these components, and then afterwards we can start to kind of develop this system into a more, let's say, spatial structural system. As I said, this is part of the ongoing research, and right now we are developing this system further. We are also, I mean, as we said earlier, this system is developed with rattan canes, which need to be imported. So we are also in EmTech looking into ways of working with willow canes, which are locally resourced. And also what is important, I mean, the reason why obviously we're interested in biodegradable systems, friction, and why we have tried to omit using adhesives is because we are working around this agenda of respecting the environment and using as many natural materials as we can to create a structural system. These are some, let's say, earlier robotic fabrication tests that we have created. So our two robots at the basement can kind of talk to each other, and we have created custom-made, custom-built end effectors for different types of bundles. Again, as I mentioned earlier, one important thing to highlight is we are working with varying stiffness in different morphologies. So we work with, let's say, bundles of, and here you can see how it fails, with bundles of 7, or like with bundles of 21, bundles of 35, so on and so forth. And of course, a very important reason why we use these kind of robotic fabrication techniques is obviously the increased control and precision. So right now you're looking at some of the kind of joinery generation with the robots and with 3D printers. Actually, I mean, what I would like to highlight here is that these elements perform actually beyond just joineries. They also guide the assembly process through their precise geometry. So they are not just joinery elements. They are very helpful, as you will see in a bit, in helping with the assembly process. And these are some examples from our connections. So these are the base connectors that have been created through recycled pellets, 3D printing, and they have been filled with sand to increase their weights.
One of the key aspects of this project was to remove any need for adhesive. So the entire project structure, the experimental structure, was standing based on friction. Both pre-tensed bundles that were coming together, the feed and the basement and the connection nodes, and also the way that they interlock to one another. If we and through this process, actually, it helps us the sequence of assembly. And this sequence assembly was very straightforward. However, when at the end, when you look at the structure, it was quite hard to understand and find out where the components are. And this was one of also the key areas of the project, to design and fabricate a modular system through which the final aggregation tells a different story.
That's us.
Us telling the story now.
So this is a very quick kind of time lapse. So this kind of covers the, I believe, final 3-4 days of the assembly process. So as you can see over there, everything is actually unflattened at first, and we're following, a kind of printed drawing, and then we're kind of bending everything into how they are supposed to be. And in that process, obviously, what is very important for us, as I mentioned earlier, are those base connectors, ground connectors, as well as the other joinery to guide us with the assembly process. Also, obviously, one important thing to mention is this system is quite flexible. And so in that respect, the joinery really helped us to stabilize the system. And anything you wanna? All right. And so this project, at its conclusion, we were invited by the UK Construction Week to showcase this prototype in Birmingham. In October, which was just 2 weeks after we had concluded the workshop. So what was quite nice about the system is that obviously you can disassemble all the components, and then just load them on a truck, and then assemble them back again, which we did with our D-Lab and EmTech students.
Now we get to I think more important topic here, and the project that we showed was an example of how complex an architectural project could be, because when you're dealing with a problem at hand, there are always multiple different goals and objectives that have to be addressed throughout different scales of investigation. This is something that we all quite understand and experience dealing with any project from any scale. And this will challenge the architect's role. The role that was traditionally about understanding and finding the singular answer to a question that was asked, to the role, with the help of a technology, Rhino, Grasshopper, one of them, to create a series of relationships in order to better understand how the problem to be asked rather than to be solved. This is a continuous topic that we explore here at EmTech and through our workshops to better understand the problem at hand and to better dissect the problem into its basic and modular components, through which, with the help of a technology, Rhino, Grasshopper, other processes and pipeline, to solve the problem in a more efficient manner.
And again, on a broader scale, why are we interested in, let's say, lightweight material systems, in biodegradable materials, so on and so forth, is as a broader agenda in EmTech, our research explores multi-scalar design. We're very much kind of interested in conducting research on issues revolving around climate change, lack of biodiversity, ecology, immigration, urbanism, so on and so forth. So we would like to conclude with a very short video of the project that we showed in the beginning. That's MacBoy. This Master of Architecture dissertation is by Luis Bossums, Rodrigo Maron, and Maxence Fromentin. It's contextualized in the Yucatan Peninsula in Mexico. This specific location faces hurricanes from May to December. And these hurricane events are becoming more devastating every year. And obviously, while major cities in this peninsula have the tools and infrastructures and policies to resist them, the indigenous rural, let's say, Mayan people and their traditional lifestyle are being affected in very negative ways. So that was the premise of the research. The research is conducted on multiple scales. First is the morphological scale that you see here. They investigated to a system, basically a habitable system for the Mayans that was formed by wind-driven form-finding processes, material experimentation, and they work with bamboo and bundling of bamboo material system.
One of the key elements in this project was information flow, how to take what has been conducted in a smaller scale, inform the larger scale, and how everything will be then tied back together to form a complete project at the end. And this was actually could be facilitated with the pipeline and the workflows that we explore here at EmTech.
Yes, so starting from the morphological scale, then they started to develop a kind of a micro-urban scale, let's say, system, an urban system, where they also, let's say, incorporated the cultural context and the living system and the economical context of the people and their activities in order to generate a micro-urban, let's say, living environment. And at the same time, they also worked on a kind of a larger ecological urban framework to create an evacuation system when these people are faced with these kinds of, let's say, very risky, large-scale flooding events. So this actually, this project is actually a very kind of, I would say, a good summary of what we are trying to establish in EmTech. Understanding the context, understanding the biome, understanding the challenges of a specific biome, and not only, let's say, environmental or climatic challenges, but also the cultural context, the economical context, how people live, and their kind of building practices as well, and later on, trying to kind of, let's say, relate the traditional building practices with novel technologies. And how these building practices can then have an impact on their cultural context as well as living context. Yeah.
This is a clear example of how different scales being investigated all at the same time. Information flows from one stage to the other, and yeah, we will end this presentation here.
Thank you, guys.
Thank you.
Thank you.
Was robotic arms eventually used for the final bundling product?
Yes, they were used for final bundling products.
I
yes.
mean, that's a very important part of the process because we need to know how much we are bundling. We need to have control over the degree of bundling and when it fails and how much we can bundle. So that's why we use the robots.
Because I've been looking for a pedestrian simulation plugin for a while now, which is free, so that's free. Just about the sociability hierarchy and the skills that you were talking about. If we were to use it in a real project like a master plan or something, the sociability parameters, is there some sort of documentation or background on what they're based on? specifically? Because from what you guys showed, it seemed like a bit abstracted and a bit black box almost.
Yeah, so during our thesis, we developed a sort of parameter base for sociability, defining them in a quantitative manner. And so we used these parameters as a basis for setting those sociability scores for each person. In the plugin itself, it is on the outside, it's an input for each agent. So you can always change this score. You can make your own way to come up with this score or choose certain parameters or not, and then input that number specifically yourself. So you kind of drive how social the agents are and also the global sociability as well.
Thank you.
My question is about the Hive as well. I know it's a bit technical, but what kind of shortest path algorithm did you use, and how did you make sure that the shortest path algorithm doesn't, consume all of the CPU power? Because I was doing ABM when I was doing my master thesis as well, and literally when I clicked the button to start the shortest path algorithm, I was using an A-star algorithm. It just basically freezes my computer. So I just want to ask, what did you guys use, and how is it, done?
Yeah, so I'm forgetting the name of the exact. Yeah, it starts it's the shortest path algorithm, the one that starts with a D. Yes, that one. So that was the algorithm we used. I think we did run into similar issues as Hive was scaled up to across the entire city, that we did run into CPU issues. So that's why a lot of the work that we did focused on segmenting the design. Particularly, we were looking at Hong Kong, so we would take specific portions of the city, analyze it at one time, and then to reconcile those differences, we then analyze those connection points between them as a sort of a post analysis, and then as a way to sort of get around that challenge.
This goes out to everyone, I think, because we all know Rhino is brilliant, Grasshopper is really enjoyable. But is there a software that you personally use to supplement or complement the Rhino software? If that's the case, can I ask what your favorite ones are, please?
Start from here. Well, personally speaking, and also in EmTech, we go to basics. So we equip the studio with the knowledge of programming. So if you need to extend the capability of the software, then we could. The other thing that at EmTech we really like recently is Unity, which is quite aligned with the overall design and workflows that we explore. Yeah, that was for me.
Yeah, I guess for myself, Grasshopper has been a quite favorite and go-to tool for me, just because of the flexibility it offers from as a student entering and being able to pick up and learn it quite quickly with the visual scripting aspect. But then as I've learned, gotten more comfortable with it and more advanced, being able to script in C# and Python, so that flexibility and now that which is starting to come out, the interoperability with other softwares has been quite powerful. So Grasshopper would be my answer.
Yeah, I think my newfound favorite is Rhino Inside, particularly with Rhino Inside Revit, because you can do all sorts of quick testing and parametric features in Grasshopper, where people maybe feel more comfortable in Rhino and Grasshopper, and then push this type of data into Revit and introduce data within each of these components to make it more kind of a seamless workflow from conceptuation into actual fabrication and design.
I'm very much interested in sub-D modeling. I'm very happy that Rhino, and to a certain extent Grasshopper, has some sub-D modeling tools embedded right now, and I really do hope that they will be more advanced in the future.
In engineering, it's a plethora depending on what you need to do, ranging from building physics to finite element method to it really depends on what you need to do. I think what is really clear is that Grasshopper is so easy, accessible, everybody's contributing, that it became a little bit centric to what you want to do. So the parametrics is usually done there, but then there's also the documentation part, and there are also other platforms when you are a little more working on the documentation workflow, like Dynamo and stuff like that, that goes into that pocket. But yeah, many.
I mean, this is probably quite specific to what we do, but a lot of the time it's bringing data from test rigs, so reading CSV files. All the make human or any kind of software, standalone software that obviously can bring anatomical data. And inside Grasshopper, probably we're quite, considering we have to create watertight B-reps most of the time, it has a computational cost. So anything that helps us smooth the process and kind of be clever about the way we do construction. So pufferfish, I think, is probably one we use quite a lot. Kangaroo, obviously, a lot for different reasons. Quite difficult to link it to simulation in the type of materials that we do, but it's not impossible.
When you were doing the optimization for the model, you were saying that the main problem was how much it's fitting the physical model. So what kind of optimization did you run? Like, were you having sensors, or what were you optimizing?
Well, it wasn't about sensors. So what we were optimizing in that instance, so in research you can find out about the Young's modulus of rattan canes, right? But because it's a natural material and there are differences between, let's say, each cane, we needed to find a correct coefficient that we could use for our structural analyses. So using the physical experiments that we had as baseline and the digital simulations as well, we had to couple them to each other so we could extract a correct coefficient that we could then use in the structural simulation. Does that help?
So the optimization was not to find the coefficient itself. Like, you were finding the coefficient from like a couple of physical models that you've done?
The optimization was to find the coefficient through making sure the digital model geometrically is as close as possible to the physical model. So what we have done, we captured the physical model, we put it side by side to the digital model and tried to, through multiple key moments of the model, to fit the digital model to the physical model through understanding what coefficient should we introduce to the physics engine. So that was the entire, because the problem and the pipeline that we had at hand at that particular phase was the kangaroo pipeline. And we needed to make sure that what we simulate is very close to what we get physically. So it was more geometrical optimization, but to find the coefficient to fit into the physics engine.
Thank you.
After you tweak it was a robotic arm, how do you prevent it from reverting back to its original state?
Well, that was one of the main challenges. I think our students can tell you a lot about this. But one of the key things was to actually come up with the proper metal ties in multiple locations to make sure we tie them quite enough in order not to roll back. And it was quite a challenge. Still ongoing research to come up with a more efficient way to make sure that this twist doesn't roll back to its original state.
Well, the component, because we're bending it in two different axes, it actually becomes quite stiff. And we use those circular elements to stabilize it even further. If you're asking about why we chose a specific morphology, was because of the fact that, yes, it is unstable. It can rotate around one axis and kind of topple. But we were interested in how can we aggregate these to create that wall system, as I explained earlier. So obviously the morphology itself is something that we are developing right now in EmTech Studio. That was the first demonstrator for us. And the reason why, as I said earlier, we thought it would be a good candidate for a demonstrator was that it is quite stiff in two directions and it can be aggregated. But of course, we're not kind of tied to the morphology. We're working on that right now.
Okay, great. Thank you everyone for showing up, and we hope that you enjoyed the wide range of presentations and projects. Now we'd like to invite you guys to that room over there for more informal conversation and more in-depth conversation about the projects over the drinks. Thank you all.